As climate change defines the evolution of society due to the combustion of fossil fuels, and ongoing political tensions lead to energy crisis, renewable energies show a clean alternative to the increasing electricity demand. Oceans present a largely untapped energy source capable of providing 20% of the UK's electricity demand. Wave energy is potentially capable of supplying the world's total yearly demand, but capacity of current projects is negligible in the global energy mix.
Their aim is to develop and test a physical platform takeoff system for the existing platform demonstrator with a 1 watt average output power, converting the absorbed energy into usable electricity. Simultaneously, options for commercial power delivery at large scale were investigated through simulations.
The objectives were met to a great level, on time and under budget. To further improve the physical system, real-time data monitoring would be implemented, and a backup supply and sensor system would be developed at the low power scale to finally integrate with the real M4 platform for wet testing.
Motivated to push technological development in this field and increase adoption in the future, this project demonstrates the feasibility of a prototype wave energy converter device, the M4 platform, a near-shore multi-float attenuator device.
The intention of this project is not to produce a commercially viable product, but to assess the feasibility of wave energy and provide solutions for the M4 platform.
The low-power physical system was divided into 3 sections: hardware-in-the-loop, generation, and energy storage. Since there was no access to pool testing, the hardware-in-the-loop system was developed to emulate the M4 platform dynamics through the use of a DC motor based on the parameters of the existing M4 MATLAB Simulink file. This was controlled by an ESP32 microcontroller with C code, which allows for data acquisition. Control system strategies for the generator were first studied in simulation. The shaft of the emulated platform was coupled with an identical motor acting as a generator, and the irregular power waveform was rectified with the embedded inverter within the motor. A splash-proof cage was built for future wet testing.
Energy storage is crucial in renewable energy systems to establish safe and deliverable power from an unpredictable source. An energy storage system was built using a capacitor bank to smooth the unconditioned input voltage. The physical system was assembled to demonstrate the potential of wave energy by powering a resistor LED load. A secondary backup circuit was designed to turn on if the output voltage reached a pre-decided critical point. This backup circuit could be connected to the load devices to maintain power during periods of low generation.
Real commercial applications of wave energy converters in the kilowatt and megawatt scale are designed to power fish farms and other marine technologies, or to be connected into the grid for distributed generation. Our simulated systems consisted of 3 sections: generation, conversion, and interfacing with the grid. 2 large-scale systems were designed at 20 kilowatt and 1 megawatt output power by scaling the M4 platform Simulink file. Several control system approaches for a permanent magnet synchronous motor were revised for the generator to maintain a 3-phase AC electrical output, which was then aimed to rectify to DC.
The next stage of the high-power system is to connect and stabilize the rectified DC output to form a stable DC link. This was achieved with the assistance from a supercapacitor energy storage system, which was all modelled within Simulink. The generator needs to meet certain criteria to connect to a national distribution network to maintain stability and control. A summary of connection requirements was gathered considering UK grid code standards.
In this project, we have achieved an M4 platform emulator for dry testing, a power takeoff system comprising generator and energy storage, high-power simulation models demonstrating the tech requirements, and a report of grid connection requirements. With future work on the low-power system, high-quality motors that fit the system requirements could be incorporated to overcome high-torque coupling problems. Then, a PCB can be developed to connect all low-power system components to integrate with the M4 platform for wet testing. We hope this project helps to understand the many challenges that come with this technology in our mission to meet the global decarbonization goals.